see if it's working. Hi, everyone. So our first presenter for today is Hannes Furmans. He's a 7th semester bachelor student at the Computer Science Department of ETH Zurich. He's also the CTO of a newly funded startup called Peer-to-Peer Industries, which was also in the batch of Y Combinator in the winter 2025 section. And he's interested in decentralized algorithms and consensus algorithms. He's going to talk about one of the works we published last year. And Hannes, I give you the stage.
Thank you. So as you said, I'm going to talk about Victima, which is about increasing address translation reach by leveraging underutilized cache resources by the Safari Research Group, and especially Konstantinos Kanellopoulos, which was presented at the 56th International Symposium on Microarchitecture. So let's start with an executive summary. The problem we want to address is a common performance bottleneck in data-heavy applications, which is data translation. And we will see that address translation, especially the page table walks, are in fact a big problem. And then we can think about if we can use some resources that are typically underutilized on those applications to store data to reduce the number of page table walks. And I will describe how this works then. And the key idea basically is to use L2 data caches and transform them into TLB entries. And the benefits are that you achieve better performance, especially in virtualized environments. And it's also transparent to the operating system and the applications, so you don't need compiler support or operating system support. And it also works with huge pages. And then finally, we will see that Victima outperforms state-of-the-art TLB designs by 5.4%, and will achieve similar performance compared to an optimistically fast 120K entry TLB. All of these words I will explain now in the background. After then, I will go a little bit more into the motivation, the idea, the implementation, and then the results, and then we can go into a discussion. So I would start with address translation. Address translation is a consequence of virtual memory. So maybe we should do a quick recap on why we want to do virtual memory. Just a brief reminder, virtual memory is the thing that a program sees a different address than the address actually used to store the data physically in the RAM. And we do this because of we can now share memory very efficiently. We can let programs communicate via memory, and it's also a security feature. And and all of these mappings I just explained, from virtual address to physical address, are stored in a thing called the page table, which is managed by the operating system, which is typically organized as a radix tree. In x86-64, it's a 5 to 4 level radix tree. And to access this page table, we perform a page table walk, which is walking down the radix tree. And the page table walk works like this. So here in the top right, I have that doesn't work, never mind. There's a memory access counter. So to keep that in mind, and we have a virtual address, and we take the first 4 9 bits and start with the first segment here, and then we go down the page, the radix tree. So for the first 9 bits, we perform a lookup in the page table and look for the radix node with the same 9 bits, which is pointing us to another page that we then access, and then recursively we follow this to finally 4 memory addresses, and then the leaf node of the radix tree, there is the physical frame that we want to know. And then we can access the memory, load data, whatever. So this is pretty inefficient. If we would do it this way all the time, then the access to the physical memory is quite slow. So what we do is imagine there's a virtual address coming from the core. It's handed off to the memory management unit, And then it tries to avoid doing a page table walk, but if this can't be avoided, it goes into the page table which lives in the memory hierarchy. So it's just a big block in the physical memory. Yeah, sorry. And yeah, so the memory management, as I already said, tries to avoid looking into the physical memory. And for that, we need another concept, the translation look-aside buffer. I will refer to this now as a TLB, but that's what it is. And it's basically a cache from the page number of the, like from the virtual page number to the physical frame number. And we, if this fails, like if the translation look-aside buffers fail, we do the page table walk. So we are incentivized that they work correctly. And how they work exactly is highly CPU dependent and of course architecture dependent. So just an example, the Apple M1 has an L1 TLB, I will explain what these are later, with 256 entries and an L2 TLB with 3072 entries. And for comparison, an Intel Raptor Lake, which is the baseline we will look at for the rest of the talk, so keep that in mind, has a L1 TLB with 64 entries and L2 TLB with 1.5 thousand entries. So now let's look at address translation flow and in more detail. So the virtual address comes into the memory management unit. The first thing we do is look in our L1 cache TLBs. We have two of them, one for instructions, one for data. And if those miss, we look on the unified L2 TLB, which is shared by the cores in the CPU. And if this misses, we take the page tail walker, which in turn has a page walk cache, which again caches like the edges in the radix tree. So the mappings from this this block to this. And if this misses, we have to access the memory hierarchy in the page table. So this is how it works now. Let's look at why that's not ideal. So the researchers conducted some studies and found that on average in those data-heavy applications, we waste 137 CPU cycles just on this address translation, which is quite a lot because it could do other stuff, computing, whatever. So let's just make everything bigger, which means we increase the address translation reach. And address translation reach is like defined as the amount of virtual address to physical address mappings that are stored in our caches or TLBs. And we have like those 2 megabytes, 4 kilobytes, because modern processors have different pages, like support multiple page sizes. We have TLBs for each of one of them. And the idea is we just make them bigger, okay? Classic engineering approach. Make them bigger, increase reach, reduce page table walks. Sounds good, right? No. Imagine we have very large hardware TLBs with 64,000 entries. So remember, that's way, way more than in our L2 TLB. That's way, way more than we currently have. Then we only increase the performance by 0.8% over the baseline, okay? And assuming realistic 39 cycles access latency, which is, you know, quite bad because we increased it by quite a lot. So yeah, it's not worth it. The alternative would be to use software managed TLBs. They are implemented by the operating system, very common in virtualized environments. And they basically work by having, if we miss the L2 TLB, we have some block in the main memory where we manage an L3 TLB. And this is a huge continuous slice of memory. It has to be implemented in the operating system, very complex, has a high latency. And you know, writing operating system is pretty complicated as it stands. And yeah, sorry, and the performance is not that good too, because we still have to access the physical memory, right? So, sorry, I need some water. So, can we store TLB entries in data caches? This is the key idea of the paper. Let's see if we can do this. Remember, now I'm not talking about L2 TLBs, I'm talking about the L2 data caches that you should all know about. In the benchmarks, in the interesting data-heavy programs we are looking at, those are the the letters at the bottom for future reference we want to know. We see that we don't reuse quite a lot of the L2 cache, so we couldn't put other things there. As you can see, there's only a very slim portion of the L2 cache we ever reuse. So the key idea is take the PTE blocks for data and turn them into TLB blocks, and thereby, doing tag matching and then accessing the data faster. Okay, typical cache behavior. Let's start with an overview of how that actually is implemented, because it's not as simple as it seems. We take the existing MMU, we have the L2 TLBs, those things don't change. But on a miss or an eviction, like we employ a new thing, the PTW cost estimator, which then decides, is this a costly to translate page? And if it is so, we put it, we take a PTE block that is not used and transform it into a TLB block, and now we're very happy. Because if we have a miss now, we have a very low access latency and we know the address very quickly. So let's talk about the detailed design. First, we have to modify the L2 cache. And then we want to go a little bit into how we decide what goes into the L2 cache, and then the page table walk cost predictor that I mentioned earlier. So let's imagine we have a data block in the L2 data cache. The first thing we have to introduce newly is one additional bit. That's basically saying, is this a TLB entry, which of course, if it's a data block, is 0. And then we have the data, the value in the key value store that the cache basically is, an offset, and a set index, and a tag. And you remember, we do tag matching, and then we get the data. And now that we want to make them TLB blocks, we have to set the TLB entry bit that we introduced to 1. And the thing we want to store are the page table entries. We need 8 bytes per page table entry. And we again have the offset, the set index, and the tag. The tag is the first 23 bits of the virtual address. And we have 13 bits to spare for some metadata. Okay. Is everyone following me up until this point? Okay, I hear no complaints, so I continue. So the first thing is, if we want to match a virtual address with a TLB block, the first thing we look at when doing tag matching is, is this a TLB entry? If yes, does the tag of the virtual address, so the first 23 bits, match with the tag in the TLB block? And then we know the offset, we take the correct PTE entry, and then offset into it, and then we know our address. Clear? Good. How do we decide what gets into the L2 cache? There are 2 scenarios on an L2 TLB miss. So again, a cache miss that we now discussed at length, or an L2 TLB eviction, which means entry is replaced in the L2 TLB. So first scenario, L2 TLB miss. So again, MMU, L2 TLB here. There's a miss happening during address translation. We ask the page table walker to look for the entry that happens asynchronously. And we also ask the PTW cost estimator, is this a worthy to store entry? This happens in parallel. When the address comes back, we see it's worthy to, or rather, if the PTW cost estimator says it's worthy to keep this entry, we transform the PTE block into the TLB block with the address we just resolved. And then we're done on a miss. Okay. On an eviction, the difference is we already kind of know the address, but we still perform a page table walk. We also run the PTW cost estimator, and basically the same process happens once this asynchronously, so we run the page table walker, but the difference is, in this case, this is not in the critical path. So the program can still keep running while this occurs. So this is a very nice scenario for us. So when the PTW cost estimator has made its decision, we then may proceed to transforming the PTE block into a TLB entry. And again, we're very happy because the next time we want to access that, it's very fast. So now let's talk about the access a little bit. So again, MMU L2 TLB misoccurs. So normally we would ask the page table walker to perform page table walk. We do this, but in the meantime, we look in the L2 cache, perform the cache matching, and we see we have a hit. And then we can abort the page table walk, return the address, and we're done. In case of a miss, again, the MMU exists with the L2 TLB. We do the page table walk asynchronously. We look in the L2 cache. There's no entry there, so we just wait for the page table walker to finish and then return the address it resolved. Okay, does everyone understand what we're doing so far? Okay. Let's continue with the cost predictor, the magic box I said we would come to. Anyway, so the key purpose is to predict if this address is a costly to translate address. And if so, we insert the TLB blocks. How can we do this? So again, in the implementation of the paper, we use two features, the PTW frequency and the PTW cost. Both of these things we know from the PTW cost walker. Those two features come into a comparator tree. We do some very quick math, and then we know if it's a costly to translate page. Very cheap, very simple. And yeah. And we know that so now it's costly to translate page, so we will store it. So in the paper, there are alternatives discussed to this approach. These are all the metrics we can collect, or you could think of more, but these are the interesting ones about such an address translation. And you see we only took the page table walk frequency and the page table walk cost, but there are many others to think of. And when I say input features, you're probably thinking of machine learning or neural networks. And in fact, that's what the author did in the paper. He looked at 3 neural networks, and the comparator approach eventually took. And as you see, the bigger neural networks actually perform better, but not that better to justify the very high cost, or very high additional area and power required. And as you see, the neural net with just 2 input features doesn't even outperform the comparator approach. So in one metric, it's a little worse, but in the other one, it's a little better. So, we can just use the comparator, just need very little additional size, but keep that in mind for the discussion later. So let's take a look at how it works in practice. How do you evaluate something like this? You could build a new CPU, but this is very expensive. So instead you use a simulator like the Sniper multi-core simulator. You need to extend a little bit with a TLB hierarchy for multiple page sizes, a radix page table walker, and page walk caches. This is all just for the baseline. And then you execute some workloads on it for 500 million instructions. These are the workloads if you're interested. They're also referenced in the paper. And then we get some results. So let's take a look at them. On the bottom, you see the benchmark. On the left, on the x-axis, you see the benchmark. On the y-axis, you see the speed up over the baseline. The baseline is at 1.0, in case you were wondering. And in the top, we have some alternative approaches, PUM TLB with 64,000 entries. That's the software managed TLB. And the other 2 ones are 64,000 entries hardware TLB or 128,000 entries hardware TLB with optimistic access latencies. So fewer than those I cited earlier. And we see with these optimistic assumptions, Victima outperforms all other solutions that we compare to. So it's faster in these benchmarks. So we're happy. In virtualized environments that I didn't have time to go into a lot, how that works with the address station there, Victima outperforms software managed TLBs, which is the go-to way to do that right now, by 12%, which is again very impressive. And remember, we wanted to reduce the number of overall page table walks. And as you can see, we can reduce the number of page table walks, which we set out to do, by 50% of the baseline. So the other ones reduce it too, so that works. But Victima is way better on average. So remember, we have L2 caches can be sized differently. If you look at the spec sheet of a processor, you will see. And we see that if we use Victima with bigger caches, like an 8 megabyte cache, we can even reduce the number of page table walks by 63%. Again, the reduction of page table walks is on the y-axis here. And you see that the reduction of page table walks grows linearly with the, actually not linearly. Anyway, grows with the size of the L2 cache. So let's talk about area and power overhead. This all sounds very complicated. Actually, it isn't. This is in comparison to an Intel Raptor Lake. We only need 0.04% more area and 0.08% more power, again, with those great performance improvements. So we're pretty happy overall because our computer is now fast and it didn't cost us much. More results are in the paper, how to do that in virtualized environments, how to maintain operations in TLB shootdowns, the replacement policy, how the comparator is implemented in detail, and the translation reach provided by Victima. Here's a QR code to the paper if you want to read it for yourself. It's also open source. You can look at it on GitHub, on the organization of the Safari group. Here it is with the simulator and everything. And it won a Distinguished Artifact Award because it's so nice and open source. Yeah, sorry. And the takeaways are Victima is feasible to the other proposed solutions, which again are kind of necessary because it's a bottleneck. It has better performance, it's transparent to software, different than the software managed TLB, and we don't need much additional surface. And the L2 caches can and should be reused because they've outgrown at least some of the applications we run on them. And although neural networks weren't used, here we can see that they might be a good idea, even in low-level and performance-critical scenarios like this. So now let's continue with the discussion. So the strengths of the paper. It's a very novel approach on how to reuse existing memory infrastructure. And it's also a new idea on how we can transform a data cache block into a TLB block. And we also see significant performance improvements, which is also, always very nice. And this happens with a very low power and area consumption. And the nice thing is it's transparent to the operating system and user applications. So, weaknesses. The contribution of the page table block cost predictor is unclear because in the evaluated workloads, the L2 cache MPKI is already very high. That means in layman's terms, the L2 cache wasn't very used anyway, so we could have just naively put everything in the L2 cache. Maybe that could have worked too. And the complexity of a TLB shootdown is increased. TLB shootdown basically means when you migrate a page table in hardware, you notify the operating system, notifies the processor that we do this migration, and operating system gives the hardware only the physical frame number. And since we index the L2 cache by the tag, by the virtual address, we now have to do basically an ON search through all of the entries in the L2 cache to change them, which is, slow. And has a very strong emphasis on x86-64, which is, a well-optimized ISA, and with a lot of caches already. Maybe some other architectures like RISC-V would have been interesting because they can incorporate a design like this maybe more easily. What is also not looked at is if an application uses the L2 cache very heavily. So the problem application would be one that uses a lot of address translation and also the L2 cache, because then you need to kind of balance between those two, and that's not really looked at. So yeah. And in virtualized environments, we need to perform a bit more tag matching because we also need to match the virtual machine ID in the L2 cache, and it's not looked at it that much. And also, like all the papers I think we are talking about here that focus on memory, there is always the potential to introduce some vulnerabilities here. Think of the recent Apple disaster for side channel attacks. It's a complicated business and it's not looked at. So ideas. Could we employ this in GPUs or other accelerators, machine learning, computer vision, whatever? Yes, people did research on this. Here, NVIDIA presented in TACO 2019, did exactly that. So people do it. And is it worth it? Is a kind of a different question, because remember we talked about the L1 cache, the L2 cache, we do all these caching of caches and then another cache. Maybe we're doing address translation completely wrong anyways. That's a question to answer, to ask. And another question is, when we increase the L2 caches, the access latency increases as well. So one thing I should have maybe mentioned earlier, the reason why the hardware L2 TLBs, why they don't grow linearly in performance with the size, is because if you increase the size, you increase the access latency. And Victima is not immune to this. Next, the page walk cost predictor. Maybe we could do some interesting things here with on-the-fly learning with neural networks. Different applications have different characteristics. Maybe the cost predictor could learn from them on the fly. There are also some interesting applications with reinforcement learning, where the cost predictor optimizes itself. But here the question again would be, what are the input features? What are the rewards? Where you or can we maybe do this in shared caches between processors or sockets? And I would still say that the neural network approach is maybe an interesting approach for virtualization right now on existing hardware, because if you have a modern processor, it comes with a neural network accelerator anyway. And another idea is, so remember, if you took the DDCA, it was talked. The professor talked about the pipelining and the critical path, and the criticality of an address translation is not really considered in the cost predictor, which is very interesting, because if it puts a lot of pressure, a lot of criticality on the row buffer, then maybe we should give it priority in the L2 cache. Maybe that wasn't clear. Ask me again, I tried better. And why are we just using L2 caches? We should do this in other places as well. Can we do it on ARM? ARM supports 4 different page sizes, but again, I'm not sure, I think the Apple Silicon doesn't. I'm not sure. Anyway, and can Victima support more than 2 page sizes like in the paper? And how would that work? And again, if we have more page sizes, the energy consumption maybe increases as well, because we need to do more accesses to the cache. And if we are thinking about L2 caches, some of you may be thinking about, why not just use L3 caches as well? Could do that, but then we need to handle aliasing, and maybe we could also store TLB blocks in remote caches, like between sockets. Like think of servers, some of them have multiple CPUs between them, or within a single socket or CPU. outside the L3 cache. So and with that, I'm done on the things I've prepared, and I'm now very curious on your input and the discussion. Does anyone have an idea, comment, whatever? Question, maybe something wasn't clear. Sure.
Thanks. So I still have a question about the cache management, and I think you mentioned this a little bit. I don't know if you have backup slides on this or not, but basically, in my understanding, like when you context switch, for example, you have to clear the TLB, and here in this case, you'd have to like, I guess, walk the cache. How does that work?
So this is a very good question. Remember the metadata I mentioned earlier? We can go back. The metadata. Sorry. Here, the 13 bits here. We use 9 of them for that. So there's a process identifier, and we just make this part of the tag.
So we don't need to clear the cache.
No, we don't need to clear the cache.
Switch. Okay, thanks.
Another question? Anyone? Comments? I talked quite fast, so it's okay if you didn't understand. Okay, then. Then I guess I'm done, or unless anyone wants to take the last chance. Yes.
This is maybe you mentioned it and I just didn't catch it. We have 8 PTEs in a single TLB block in the cache. Does that mean that we have to evict PTEs from the TLB in blocks of 8 at a time? Or like what if only one of the pages is in the TLB when it gets evicted from the cache, from the TLB?
Yes, that's a good point. Maybe I should have made this more clearer. You're right. From the eviction, we only have the one PTE entry. That's why we need to perform the page table walk in parallel to do that, right? And then we just store multiple of them. Maybe good that you remind me. In contrast to the L2 and L1 TLBs, where you have one virtual address and you match that to one PTE. In Victima, you match multiple potential PTEs to one tag. Anyone? Okay. Am I done? Oh, sorry.
So what could happen in the case that the L2 caches are private across processors, and then how does cache coherence come into the picture? Because if you have some blocks that evict or modify data in a cache line, and they send invalidation messages across the bus, you lose on the benefit of storing these entries in the L2 cache, L2D cache.
So I mean, if another process evicts a TLB entry,
invalidates
the
cache line,
yeah, then we lose it.
We lose that entry.
Yeah, I think so.
Or is this a baseless question? Because
So if you have a private L2, then you're the only process, right, that's running using that L2.
that's right. And
If the only scenario that you will evict, the scenarios where you will evict a TLB block is that if I need to evict something from the L2, that's one, which is handled normally. You simply do not put it anywhere, the TLB block. And the second scenario, which is very rare, and I'm not sure if it's possible in the processors right now, is if you have a coherence eviction, which means that I cannot find, so I basically, no, not even in this case, because, because we do not store it in the LLC, in the directory, right? These are opportunistic data. So you do not care about what happens when in terms of invalidations, for example. If you invalidate the cache line that the data is pointed by, then it doesn't matter. You can still use this translation. There's no way you will invalidate the TLB block.
Even if it's shared across different processors and they update, or are you saying it's impossible for this entry to be updated?
So it's not impossible to be updated, but it's not using the normal coherence. So the way that you update this block is that you typically, the OS changes, let's say, the mapping. You have a migration, and then you need to update the physical page number. But to do this, you simply need to flush and invalidate this entry with a TLB block, which goes back to this question on how you invalidate the entries. And the mechanism is basically that you perform the tag matching and you invalidate the entry from the L2 cache. I mean, this is more complicated than what I said right now, but that's the core mechanism, that the OS would trigger the invalidation when you migrate a page, for example, and then you would handle it down at the cache level.
Thanks.
Thank you. Anyone else? Okay. How do I turn this off?
You can also use a pointer. Yeah, I make it. So it's good.
I won't move it any further because now it's still like in the light. Yeah. Yes. Yes. Thanks.
Hi again, everyone. So the second presenter for today is Benjamin. Benjamin is a last year student in the computer science department. And today he's gonna present a second work which we published last year, again on the same topic. And Benjamin, you have the stage.
Right, thank you. So I will present to you Utopia, fast and efficient address translation via hybrid restrictive and flexible virtual to physical address mappings. This was also presented by Konstantinos at Micro 2023, just like Victima. And we will see now, oh, I can't skip somehow. Is this working now? Oh yeah, okay. We'll see right away that the problem which Utopia is tackling is actually the same problem as with Victima. So it's the address translation latency from conventional virtual memory and also the large interference in the memory hierarchy. And the goal is also to improve the performance and reduce the latency of virtual to physical address translation. But the idea behind it is quite different. So here we employ two types of segments, restrictive segments and flexible segments, where restrictive segments do perform address translation using a hash-based approach, and flexible segments do address translation using the conventional page table, radix page table-based approach. So the key challenges then are, now that we have two mechanisms to translate page table data or page addresses, which pages should we place in restricted segments and which should we place into flexible segments? How do we maintain restrictive segments? And also, how do we integrate Utopia in the common address translation pipeline? So the key results which we'll see are that it outperforms the next best state-of-the-art translation scheme by 13%. Also, it achieves 95% of the performance of a perfect TLB reference model. And all of this is achieved at very moderate power and area overhead. So yeah, let's dive into the outline of this talk. First, I'll give some background and motivation, although we'll go through this very briefly because you've seen most of the stuff in the presentation about Victima already. Then I'll explain the mechanism behind Utopia. How does it make it work? We'll look at the evaluation of the performance, then see some strengths, weaknesses, and later have an open discussion about it. So yeah, background motivation. Let's recap quickly why we want virtual memory. Actually, we will recap this now because we will use some of the functions that we wanted for on the way and regain them later with Utopia. So virtual memory, first of all, gives the programmer an interface to a huge range of contiguous addresses. So it makes the life of a programmer much easier. It enables process isolation as well as resource sharing between processes. And also the ISA can define a unified address space. So it makes the code actually independent of the microarchitecture and the memory hierarchy. So we've already seen in the last presentation that this is achieved using a mapping from virtual to physical addresses. And this mapping is fully associative, which means that we can map any virtual address to any physical address. And Utopia questions whether that is really necessary. How can we discover the mapping? Well, we use a page table, as we've previously seen, that maps from the virtual address space to the physical space. And this is implemented using multi-level page tables, which are stored in memory. And we need multiple sequential memory accesses per translation, which induces the high latency. And also we need one page table per process. So page table data is really huge with this approach. As we've seen, we divide the virtual address into these bit segments to translate them, which index nodes, which are represented by page tables in memory. And from each table, we get a reference to the next table, which creates this tree data structure that we can traverse by using the indexes from the last table to finally get the physical frame number from the last page table level. Okay, So why the high latency? Well, we always have to go to memory in the worst case to retrieve a page table entry to get to the next level. So to get these indices, and yeah, we have to, for x86, for example, perform 4 sequential memory accesses. And as we already, probably most of you know, going to memory, to main memory is very slow. So we will see in the next slides how slow it really is. But first, to tackle this problem of the sequential memory accesses and to make it a bit faster, we have a memory management unit, which performs all of this for us. So we don't have to do it in software, we do it in hardware, which makes it a bit faster. Also, the memory management unit features table look-aside buffers so that we don't have to perform a page table walk all of the time, which are like caches for page table data, and also we use page walk caches. So the way this looks in hardware is we take the virtual address. We first of all try to look up the physical address in the L1 table look-aside buffers, which are separated for data and instructions. If we get a miss, we look up the unified L2 TLB. And if we miss there, then we inform the page table walker to perform a page table walk, which will first of all use the page walk caches to try and look up entries of intermediate results. And if that fails too, then we have to go to the memory hierarchy to look up page table entries. Okay. So another thing, when we finally retrieve our physical page address, then we have metadata, which tells us whether the page is actually stored in DRAM, and if that is the case, we can just access DRAM to retrieve the page. Or in another case, it might be stored in swap because DRAM is full. So the swap space is a section of our hard drive disks that we can use to extend DRAM. And if the case is that DRAM is full and the page is in the swap space, then we first have to swap it into DRAM, which means loading it into DRAM, and then we can retrieve it from DRAM. Okay. So we get this nice interface to the programmer when using virtual memory, but we pay for it by very high latencies, which, for example, for elastic cuckoo hashing, which is actually a very state-of-the-art approach also, and outperforms radix page tables, but still we have an average of 86 cycles across 11 data-intense workloads where this was measured for performing page table walks. And also frequent page table walks lead to high inference in the memory hierarchy because they may actually occupy space as we've seen with Victima in the data caches as well. And actually, for example, in the L2 data cache, page table data may occupy up to 38% of the space, which might be a problem if we have interference. Yeah. And also we get increased row buffer misses because page table walks usually access very sparse data in the DRAM. So they are usually not allocated in the same DRAM row. So we get row buffer misses all of the time, up to 30% more compared to a perfect TLB model where we don't have to perform page table walks at all. Okay, so let's have a closer look at how high the performance overhead is. So compared to the perfect TLB model, we actually, so with a perfect TLB model, we would get 31% performance speed up. So we can clearly see that there's a lot of room for improvement. So what we can see here, this is the mean over the workloads on which this was measured. So how can we make address translation faster? Well, a possible solution is to limit the flexibility. We don't have to use a fully associative mapping. We could also use a hash-based approach where we map our virtual addresses through a hash function to obtain a physical address. And that way we would drastically reduce the size of the translation structures because we wouldn't need page tables anymore. This could look like the following. So we take a virtual address. For example, in this case, the hash map would map the address 00110 to 0010. Okay. What are the pitfalls with this approach? Well, the limited associativity makes us lose some of the core VM features actually, because how can we do data sharing if we cannot choose our mapping? So data sharing with page tables is enabled by letting one process store a different virtual address to the same map to the same physical address as another process, but now we cannot freely choose anymore which physical address we want to map to, so we lose data sharing. Also, we might have increased swap space use, and this is actually the case heavily, because we may actually have a lot of DRAM space empty, but we cannot fill it up since we cannot choose what locations in DRAM we want to map to. Okay, so let's see another statistic on how big this problem really is. So in mean, over all these data sets, we have 2.2 times as many swap space accesses if we use a only hash-based approach. So this is from another paper where they used a hash-based approach only. So we can clearly see that the restrictive mapping alone is not a sufficient solution to address translation. Okay, so yeah, let's get to what Utopia does. It introduces two ways of translating addresses via flexible segments and restrictive segments. So we divide our memory into these parts where flexible segments utilize the physical memory space efficiently to get over the problem with increased swap space usage. And also we enable legacy VM features because flexible segments basically still use the page table-based approach. And restrictive segments, on the other hand, they use a hash-based approach, which enables fast translation and reduces the interference in the memory hierarchy, namely filling up the caches with page table data. So let's look a bit closer at these different segments. So here we can see a outline of the idea of the restrictive segment, where we get a virtual page number, map it through the hash function, and thereby obtain the physical page. And a parallel mechanism, the flexible segments enable us to still use the page table to get to our physical page. Okay. And yeah, as I said, the drawbacks are as mentioned. So now we can actually use the segments according to our needs for these pages, and then we can get both advantages of the two approaches. Okay, so let's have a closer look at the restrictive segments, since these are the novelty in the paper. A restrictive segment is similarly organized to hardware caches, actually. So it's organized in a set associative manner, where virtual addresses mapped onto sets, and these sets are M-way associative, which means that they can store up to M entries, just like with hardware caches. And also Utopia allows the use of multiple restrictive segments so that we can actually be backwards compatible with huge page mechanisms where we have different page sizes. Okay, further, we look at the structure of how this works. So we utilize a data structure called a tag array, which stores the tag of a virtual address and some metadata of the page table entry. And we utilize this by looking at the hash value, which gives us the set in the tag array that we want to access. And inside the set, we perform tag matching, just like with hardware caches, to see whether this virtual address actually belongs to this restrictive segment. And to further speed up the process, we introduce another data structure, which is the set filter. And the set filter is basically just a number of counters, one counter for each set that stores the number of entries of that set. And this we can use because if the counter for a set is 0, which means that there are no entries in the tag array, then we can skip the tag matching, because this is a very expensive operation in hardware, because we have to perform M equality checks at the same time in parallel. Okay, so this is the basic idea. Now let's look at the flow of how this works out. How do we translate a virtual address? So first of all, we get our virtual page number. Then we map it through the hash function, access the set filtering data structure, look up the set filter counter at the appropriate index from the hash function. And if it is not 0, then we perform tag matching. So we access the tag array, look up if our virtual page number tag is in there. And if that is the case, well, we have actually already retrieved the physical memory address, which is just given by the base register value of this restrictive segment. Then we add the set index times the associativity to go to the right set. And there we add I, which is the ith way where our tag was stored in the set. Okay. So let's look at the broader picture. How do we integrate this with the flexible segments? First of all, we try to access the L1 TLB. If we get a miss for our virtual page number there, then we access the restrictive segments in parallel. Oh, no, sorry, not in parallel, depending on the size. And we also access the L2 TLB, and we can choose whether we want to do these two at the same time or in a sequential order, where we first access the restrictive segment and then the L2 TLB. And if we get a miss in both, then we perform a flexible segment walk, which is basically just looking at the page table as in the conventional radix-based method. Okay. So in the end, we always obtain our physical address. So now we created a new challenge by dividing the memory into two kinds of blocks, namely, how do we allocate and how do we migrate between those segments? Because we have to choose where our pages should go, in a restrictive or in a flexible segment. We do this using the allocation using page fault-based allocation, which means that if we get a page fault for a page, we immediately allocate it in a restrictive segment if we have space there. If we don't, then we allocate it in a flexible segment, so in the page table. What about migration? When do we choose to migrate segments between a pages between a flexible segment and a restrictive segment? So we use the same page table walk tracking based cost estimate actually as proposed in Victima to estimate how costly to translate pages are. And based on that, we can define a threshold. And if the threshold for a page in the flexible segment is reached, so we identify it as a costly to translate page, then the OS is informed and can perform a migration from the flexible segment to a restrictive segment so that we can do the address translation for this page faster in the future. Okay, so what does all of this look like in hardware? Basically, it is very similar to what we've just seen from the data structure view of this. So we still have the L1 TLB, which is accessed first. If we get a miss there, then we go to the restrictive segment walker, which is basically just a finite state machine accessing the tag array. And additionally, we introduce a tag array cache and a set filter cache so that we don't have to go to memory all of the time to perform the tag array accesses. So this is just a further speed up. And in case we get a miss there too, or then we can, oh, yeah, sorry, this was actually explained here. Okay. Yeah, and if we get misses in the tag array cache and the set filter cache, we have to go to memory hierarchy to look up the tag array data. So the flow is now the following. We first query the restrictive segment walker. And meanwhile, we can decide to stall the L2 unified TLB to save some energy, or we can look it up in parallel. But if we stall it, then there is the case where this in the restrictive segment. So in this case, we immediately get it from the restrictive segment walker. And there's another case where it's not in the restrictive segment. Oh, and we don't have to access the page table walker, obviously, in this case. So this saves a lot of time and energy. And in the other case where it's in the flexible segment, we query the restrictive segment walker, stall the L2 TLB meanwhile. We don't find it here, so we look it up in the L2 unified TLB. And if we don't find it there, then we still have to ask the flexible segment walker to perform a page table walk. Okay, so what is the software integration that we need to enable all of this? Well, the software handles actually all of the following mechanisms: the creation of restrictive segments at boot time, because as we have seen, those have to be allocated in like a contiguous order. And if we do this at boot time, we actually save some time during runtime. Also, it handles the data allocation in the restrictive segments, which is invoked by the interrupt handler from page faults because we use page fault-based allocation. We handle the eviction from restrictive segments to flexible segments, where the OS can actually freely choose the replacement policy. And we handle in the OS the migration from flexible segments to restrictive segments, and we get informed by the MMU. The CPU gets informed by the MMU via an interrupt that costly to translate page has been identified by the estimator mechanism. Okay, so let's look at the evaluation. How does Utopia perform? For this, also the Sniper multicore simulator was used, just like with Victima. And in this case, it was also extended with a page table walker and page walk caches. For the radix page table evaluation, it was extended with the buddy allocator for the allocation of restrictive segments, so that we can simulate this. And it was extended to also simulate migration latency. The workloads that were used to evaluate Utopia were GraphBig, Access Bench, GUPS, DLRM, and Genomics Bench, which basically all of them are very translation-intensive workloads. And also, this simulation can be replicated or extended easily because it is all open source. You have the GitHub link here. Okay, so the mechanisms that were evaluated are, apart from the radix-based or radix page tables with huge pages enabled, so that we can compare this with the huge page mechanisms too. The POM TLB, which is a software-managed TLB model, elastic cuckoo hashing, which is a state-of-the-art hash-based page table, redundant memory mappings, which is also a very state-of-the-art contiguity-aware address translation mechanism, and Utopia with 512 megabytes of restrictive segments, and we had restrictive segments for 4 KB and 2 MB page sizes. And also a perfect TLB reference model to kind of have an upper bound on what we could achieve with address translation latency. Okay, so what do we see here? This is the performance actually. So we see that we outperform redundant memory mappings by 13%, which is the second best other state-of-the-art approach. So this is significant performance increase. So this is the mean value for all of the evaluated workloads here. And the red line is the speed up over radix page tables. So yeah, we get 24% in single core mode and 28% in quad core mode performance increase for over the radix tree page tables. The reason why we have this performance increase is actually the desired translation latency reduction. So we reduced, or Utopia reduced translation latency by 63% over the radix-based page table and by 14% over redundant memory mappings. So this is where it comes from. And yeah, that's what's also shown in this figure here. This is again the mean reduction in translation latency over the radix page tables. Okay. Also, another reason why we increased performance is because we increased memory efficiency. So we did, in fact, reduce row buffer conflicts with Utopia by 20% over the radix tree page tables and by 9% over perfect table lookaset buffers. And what we can see here in red is again the reference, so the baseline of the radix page tables. Yeah. Further analysis of the structures used in Utopia shows that the tag array and set filter caches are very effective. So the tag array structure has a hit rate of 81% and the set filter of 98%, which is quite well. Also, we see a very low number of page migrations. So we only see 0.8 migrations per kilo instructions, which is also obviously a very low number of migration events. So we can also see in the further analysis, they showed us in the paper that actually the page migrations do not introduce heavy overhead at all. And 82% of these page migrations are actually evictions from restrictive segments to flexible segments, which indicates that the eviction policy works quite well. Yeah, we also have a noticeable benefit from parallel L2 table look-aside buffer lookup and restrictive segment walks, because in Utopia serial mode, we have 21% performance increase over radix tree page tables, and in as I showed previously, we get 24% actually if we enable the parallel lookup of the L2 TLB and this restrictive segment walks. So also analyzed in the paper, which I will not go into detail here, is the effectiveness of restrictive segments replacement policy, also the effectiveness of discovering costly to translate pages, the sensitivity to the size of restrictive segments, which is actually quite important. So it has to be large enough for Utopia to work efficiently. And also the effect on non-translation bound workloads, where we can actually see that Utopia has a very minor, so we can observe a very minor performance decrease with non-translation bound workloads, but it's not really significant. Okay, so now let's look at the strengths of Utopia. Well, it definitely opened up new directions. This approach that you use two kinds of translation mechanisms in one virtual memory system this is the first time that this has been done. And I mean, it enables us to look at a lot of new problems. For example, the migration policies, where we can definitely choose from a lot of options. And also the performance and cost is definitely at a very good ratio. So 24 to 28% performance increase is very significant. Utopia outperforms other state-of-the-art alternatives. And it comes very close to a perfect TLB reference model. So there's not a lot of room for improvement left. And also, yeah, the paper shows a very comprehensive comparison against prior works with they also simulated other state-of-the-art approaches and compared it very well. And we can see that the hardware implementation of Utopia costs us very few in terms of area and power. So these overheads, 0.64% and 0.72%, this is not a lot, I would argue. And yeah, so also another strength of Utopia is its applicability, because it extends the MMU. It's independent of the CPU, for example. We could also employ it with GPUs or other chips. And it's also independent of the memory hierarchy. So it's modular and therefore can be applied to a lot of architectures. Okay, let's continue to some weaknesses of Utopia. So the integration costs are probably very high because we have to make changes to software and hardware. It drastically, I would say, increases the complexity of the architecture. So it would probably be very expensive to integrate in chips and OSs. And it requires coordination between OS manufacturers and chip manufacturers too. Although, yeah, the increased system complexity, this is a relative weakness, I would say, because if we want higher performance and we don't want to pay for it with higher power consumption or more area, then yeah, we probably have to increase complexity. Also, another weakness are the security aspects, which haven't been analyzed in the paper. And actually, Utopia opens up a possible side channel, which is the translation latency, that leaks information now about the location of data, because restrictive segments perform much faster address translation. So an attacker could actually use this side channel to infer information about where data lies. Also, the data migration, which is now necessary because we use two mechanisms, is an obvious drawback. So yeah, maybe there could be cases where data migration increases the tail latency of some applications. This hasn't been shown in the paper, but I think we could definitely construct workloads where this is artificially blown up if we always just hit the threshold of identifying a costly to translate page and then never access it again. Well, page migration will become a significant drawback. And also the restrictive segment size is fixed. So this could be changed. Maybe they should be dynamically resizable, which is not the case. So the restrictive segments have to be allocated at boot time now because we cannot dynamically resize them. And this is another drawback, obviously, also because if we have multiple page sizes available, then we have to perform lookups then we have to have more and more restrictive segments with different sizes. Okay. Let's continue to the discussion part. Or are there any questions so far about the mechanism? Yes.
Well, not the mechanism, but do you think that this partitioning of the physical memory could cause any concerns with the fragmentation of the DRAM? Like, can it make it worse?
The partitioning, yeah. I mean, the thing is that we can use the flexible segments to fill up the gaps pretty well, I would say. So external fragmentation is probably low. But of course, we might have internal fragmentation in the restrictive segments. So that's definitely a problem.
Thanks.
Okay. Sorry.
Yeah, I still had a question about how shared libraries are handled. Like, can the OS mark this beforehand, for example, so that it's automatically put in the flexible segment?
Yeah, shared pages are marked as such in the page table entries. So you have a whole lot of metadata bits. And if it is shared, that is marked. And then it obviously can't be transferred to a restrictive segment, or it has to be duplicated because, both processes cannot access the restrictive segment page under a different virtual address, obviously. Yeah.
Actually, I had a question as well. In comparison to the paper that we saw in the presentation before, the power and area consumption is actually significantly higher. Do you maybe know whether this is mostly because of the introduced caches?
So my guess would be that it's actually because we generally introduced a lot more hardware, and also we introduced the tag array structure. So I didn't see an extensive analysis of where the power consumption comes from component-wise. But my guess would be that the tag arrays are probably the most expensive ones in terms of power, because this is very similar to how hardware caches work. And I think that these tag matching operations, where you have to compare M equality checks at the same time for an M-way associativity, is very expensive. But I'm not really sure. Maybe Konstantinos, can you say where it comes from?
Yeah, mainly like because the tag cache and the set filter cache are like, if I remember correctly, like it's 4 kilobytes together, and this is compared to the L1 cache, it's 4 divided by 32, right? It's 32 kilobytes, let's say, the L1 cache. So this is a lot of area per core. A lot means 1% almost, right? But it's not negligible for sure.
All right. Yeah.
That's where it comes from.
I mean, yeah, I mean, this is a philosophical question maybe, but like, is the increase in power consumption a lot, or is it not a lot? Because I mean, technically, you could also argue that today we actually want to decrease power consumption. So if your architecture actually increases power consumption, yeah, that might, like, even if it's just a bit, it might seem a problem. But I guess it's a trade-off between performance and power consumption. Yeah. So yeah, first point of discussion: how high are the obstacles to implement Utopia in real systems from the perspective of OS and microarchitecture developers, and what could be possible problems with backwards compatibility? So I guess as I already mentioned this in the weaknesses, I think that the cost to implement it would probably be very high, because you have to coordinate between the OS developers and also the hardware developers, so they have a working architecture. So this is probably very complicated, and on the other hand, the drawback from having to do a lot of work in the OS can also be seen as an advantage, for example, because we can choose the eviction policies in the OS. So this makes it more flexible if we don't do it in hardware, I guess. Also, yeah, how does Utopia compare to alternative proposals? And could Utopia and Victima be integrated together? What could be possible conflicts? I'm mainly bringing up Victima because I knew that it would be presented right before Utopia. So I don't see a lot of problems there. I think they could be integrated together, which would definitely increase the performance improvement, and this would make for a good architecture, I think. So I don't know if this has been tested yet, though, Utopia and Victima together. But yeah. Also, what would be the impact of a possible dynamic resizing of restrictive segments, and how should we do it? So should we dynamically really resize existing restrictive segments, or should we just create new segments with a flexibly choosable size? So I guess the advantage of this would definitely be to reduce fragmentation, internal fragmentation in the restrictive segments. Well, if we choose to resize them, that would probably be the better option, because if we create new segments of different sizes, then we'd have to look up all of them if we want to find data in them. So yeah, that is probably what is the trade-off in terms of translation latency? Probably if we would create new segments, the translation latency would therefore increase. Okay, so on the other hand, dynamically resizing segments it might be complicated. I'm not sure entirely of the implications and how this could really work. Maybe somebody has a good idea. Yeah. Another point is how can we use a hash-based mapping without using restrictive segments? And can we devise a single segment that uses both a hash-based and a flexible mapping at the same time? So it might be possible not to divide the memory into two types of segments, but apply the two translation mechanisms for the same memory region. And this way we would completely spare all of the migration events and everything and the complexity that comes from that. Yeah, again, it's not really clear how this could look like. But basically, maybe we could perform both at the same time. And yeah, okay. Also, yeah, how about we use a better hash function that minimizes underutilization and employed across the whole memory? So this has been done, actually. This is a only hash-based approach, mosaic pages, where basically we use two hash functions. So we use one hash function to map pages into physical memory. And if that space has been occupied before, we default to the other hash function, which maps to another part of the memory. And this way we can use a hash-based approach only effectively, maybe. But yeah, this is from another work. So, but it might be effective as well because it brings this balance between associativity and underutilization. And I mean, we could obviously always use more hash functions and divide the memory further here. So it's a totally different approach, but promising too. And yeah, what are the security implications? What could the side channel attacks look like? Maybe apart from the latency side channel, there could also be other side channels. This is pretty much unclear because it was not analyzed in the paper. But we would definitely have to do more work, I guess, to show that Utopia is secure in terms of side channel attacks. But yeah, I mean, this is I guess, as has been mentioned, a common problem with novel memory architectures. And yeah, could we leverage Utopia to perform fast address translation in systems with very large memory? I guess it scales well, I would say. It's definitely scales better than the approach that we've seen with Victima, because we cannot simply increase caches indefinitely. It will induce latency again and also huge power overheads. And I guess that Utopia definitely scales much better with large memory systems. So yeah, it's basically another advantage too. So yeah, that's it. And here you have the GitHub link to the repository for Utopia. Any questions or input for the discussion?
So I was still wondering like about the determinism of the hash function. Like, first of all, is this the case that it's deterministic? Like that could be like an attack vector, I guess. And then also if different cores use the same hash function, then maybe you could get some sort of conflicts. I'm not sure.
Just to make sure, you're talking about Utopia right now, not about the other paper, right? Yeah, okay. So the hash function is deterministic. And actually in the paper, they used multiple hash functions. And it was also shown that performance-wise, the hash function doesn't really have any implications. So the one that was analyzed in the simulation is, I think, just taking the modulo. So yeah, it is deterministic. And sorry, what was the question regarding multiple cores? And
yeah, I wasn't sure if this could be like a problem.
I mean, the way I understand it, multiple cores would use different restrictive segments. So I think there can't be any conflicts from there. Yeah.
So I'm not sure if I understand these points correctly because I'm not used to this topic, but if you use a hash function, is it possible for multiple virtual addresses to correspond to a single physical address?
Yeah, absolutely. But that's why we used a associative, or why they used a associative tag array. So this is not a problem unless all M ways are filled up. And if that is the case, we have to default back to the flexible segments and use the page table. Yeah. Okay. No further questions? Yeah.
Yeah, you were talking very briefly about potential security problems with side channel attacks. So in Victima, it's like mainly about predicting some memory behavior of another program. What do you see as the attack vector with Utopia?
So basically, because of the translation latency difference, depending on if the data is stored in a restrictive segment or in a flexible segment, you can just induce from the latency that your memory query has where it is stored. So I guess, so I'm no expert on side channel attacks, but I think probably usually when there's a way in which the system leaks information like this, you can like refine it and I don't know, perform a lot of trial and error search, and then you can infer more information from this, like where exactly it might lie. Yeah. Okay. I think we're finished then.
Please contact your mentors earlier and make sure you will have at least two meetings with your mentor to get the feedbacks, unless you will not allowed to give the presentation. That's all. Have a nice day.